let's talk about the Millikan experiment. I kind of forget how to spell his name. I think it's like this. Okay, there, that's better. That's how you spell Robert Millikan. Okay, so Robert Millikan is famous for finding the charge on the electron. So when we hear about the electron, we often associate J.J. Thomson with the electron. But actually, J.J. Thomson found the charge to mass ratio, okay, on the electron. Okay. Just as a reminder, going back in time here a little bit, J.J. Thomson is associated with the plum pudding model of the atom, right? Where his idea was the atom was a positive charge with little negative corpuscles spread through it, right? And what Thomson was able to do as well, he was studying these negative charges that you could pull out of the out of metals using cathode ray tubes. Okay, so cathode ray tubes are evacuated cylinders with electrodes on either end that you hook up to a high voltage. Okay, and what happens is beams of electrons will flow across here, and then you experiment on them, right? You test them with electric fields, and you see what happens. Well, they must be negative because they bend this way, and then you put like magnetic fields on them. It turns out they react to magnetic fields, right, north and south. You can also make them bend. So by varying the strength of an electromagnetic field and the strength of an electric field, J.J. Thomson could figure out the charge to mass ratio on the electron. But that does not mean that people knew what the actual value for the charge was. Okay, it took the Millikan experiment, which happened years later, and I'll find dates just here in a second, to actually get what the true charge on the electron was. We call this the elementary charge, and its symbol is E, and its value is 1.6 times 10 to the negative 19 coulombs. It's a really small amount of charge on an individual electron. And by the way, this is equal to the elementary charge on a proton. It's just that this is a negative charge and the proton has an equal amount, but it's positive. These two things attract each other. Negatively charged and positively charged attract each other. So time-wise, this happened circa 1897. And when we look at Millikan, his was done around 1909. Okay, so separated in time just by, 12 years, something like that. So let's talk about the Millikan experiment. So this is what Millikan essentially did. Here's a picture of his apparatus. I'm just going to explain what this is all about. So the first thing you'll notice is that this is a pressure vessel. It's actually built to withstand atmospheric pressure because Millikan drew a hard vacuum inside of here. Okay, so these experiments have to be taking place under vacuum. So before we get there, let's just do a quick little review. Just as a review, okay, we test electric fields with a positive test charge, and we draw their fields based on what kind of force, what direction the force would be applied to a positive charge. So something that is statically charged positively has its field lines pointing out, because a positive test charge would always feel a force away from it. And the opposite is true of a negative. All these arrows would point in. So the next question then is, what does a field look like if I were to take two metal plates, place them some distance apart, and hook up a power source to them? Positive and negative. Well, what would end up happening is there would be a positive charge built up here, a negative charge built up here, and if I put my test charge like anywhere in here, no matter where I put it, it would always feel a charge from away from the positive and towards the negative. So inside this parallel plate system, we get a uniform electric field. Okay, in other words, it always points directly from one charge or from one plate to the other plate, from the positive to the negative, and it might bow out a little bit at the end. So no matter where I put my test charge in here, it would feel this kind of force. So this concept, this parallel plate system, is the basis of Millikan's experiment. So what did he do? Well, he took a parallel plate system, just like this. Let's see if I can draw a little bit of a nicer one here using my tools. Let's see. That's way better. Okay, so he's got a parallel plate system. All right. Which he can vary the voltage of. Get what the symbol for variable voltage looks like. It might be like something like this. Whatever. He can turn the voltage up and down, right? So that's how much and how strong the field is. So you can vary the field strength. That's what we care about. This field strength is variable. Then he placed this whole thing inside that type of pressure vessel that we saw, this big metal like container like this. Okay. And then he put a vacuum pump on it. So let's draw that like this. I don't know what a vacuum pump looks like. Let's say vac. Okay, and this sucks all the air out. So far, so good. Then he put an atomizer on here. So an atomizer is like one of those old school like perfume sprayers. You can see it right there. You know, squeeze the little ball and perfume shoots out of it, right? An atomizer. The purpose of this was, well, he filled it with oil. Okay, he filled it with oil, realizing that as it went in here, or in some way, I'm not sure exactly if it just naturally happened or if he had some other way, but he statically charged little drops of oil that kind of flew into this system through the atomizer, okay? So what he did was let's say he added electrons to them. So each one of these has a negative charge. Well, what's going to happen is we start to analyze the forces at play here. There's going to be an electrical force upward on all of these. Okay. And there's going to be a gravitational force downward on all of these. Oh, I don't like it. It's the same color. Let's do this color. A gravitational force downward. Now, the heavier the object is, the higher the gravitational force, and the more electrons that were pulled off of here, the stronger the upward force would be. Okay? So we've got a balance of force between Fe upward and the force of gravity downward. Okay? Now we know from our studies that we can solve for Fg by finding the mass of something and multiplying by the acceleration due to gravity. We also know that to solve Fe, we can just say it's Q, the charge, times E. Okay? So what did Millikan know? Well, on the back of this, okay, he would have had a ruler. Okay, he would have had a ruler. Lines. So what he was able to do with that was by looking in here through like a little telescope thing, or a microscope, I guess. Just put your eye here and you look in. You're able to see these oil drops against this background. So what you can do is you can figure out what the diameter of these drops is. If you know the diameter, then you can figure out the volume, right? How do you find the volume for a sphere, a spherical object? Should be, is it not 4/3 pi r cubed? So you know that, and then if you know the density of the oil, right? Remember that density is this, right? So I'm just going to review here a little bit. Density is mass over volume. Density is mass over volume. Okay, well then mass should be equal to density times volume. So he could get that the mass of this oil drop is 4/3 pi r cubed, right? That's its volume, times the density of oil, which is, you know, X grams per cubic meter, or, you know, kilograms as the case may be. So you can do that without actually like weighing these directly. If you know the density and you know the radius, you can figure out how much they weigh. If you know how much they weigh, you can figure out what the downward force is, right? And if you are the one creating the field strength, and exactly how you calculate the field strength is slightly beyond this, but if you know the distance between the plates, and you can vary the voltage and know what the voltage is, you can figure out what the field strength in here is in newtons per coulomb. Actually, I shouldn't use that curly E. That actually means permittivity. Let's just switch out and use the other E. Just use this E. Okay, the electric field strength in newtons per coulomb. So we can know that. So of all of this, we can know this, 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 oops, no, sorry, not that, and this. And we could say this, if we vary the voltage until one of these sits still, let's say it was this one. Let's say we varied the voltage till this hung paused, suspended in space. If it's not moving, we know that the net force must be what value? Right, F net equals 0. In other words, the upward pull and the downward pull must be exactly equal to each other. So when a drop is stationary, comma, Fg, the force of gravity, is exactly counteracted by the upward force. And of these things, we know everything, but what we're trying to find is Q, right? We want to know the charge on an electron. So how are we going to do that? Well, we'll say mg must be equal to Q times E, and we will solve for Q. Q equals mg divided by E. Sorry, I keep using this curly E, force of habit. This is how we were showing field strength, but I realize it's not a good way to show it. It means something else. We should be just using the big E. Doesn't mean energy, it means electric field strength. Okay? So how did Millikan actually figure out what the charge was, the elementary charge was? So as you can, I'm sure, imagine, we're dealing with drops with some significant mass in them. And so what that means is the electric charge must be fairly strong. So what that means is multiple electrons have to be added to these things or stripped out. I mean, if we reversed everything, we could do it the other way around, right? So we know that there's more than one. There's always more than one extra electron in these things, right? So what Millikan did was he ran his experiment many times, okay? And he found different values for Q, just many times, hundreds of times. And he kept finding a different value for Q. And then what he did was he worked out what common factor do all of these have? What is the common factor that they all have? Eventually, after many versions of the experiment, he worked out that it's that 1.6 times 10 to the negative 19 coulombs, all right? If you don't quite get that, here's another example, okay, to help us think about this. Let's imagine that we have envelopes, and we have like many envelopes. And inside the envelopes, we have paper clips. Okay, let's just say we have paper clips inside here. But you cannot tell how many paper clips are in each envelope, right? So this one might have like 2 paper clips. This one might have like, we don't know, it has some amount. This might have question mark paper clips. Let's say that this weighs 4 grams. This weighs 8 grams. This weighs like 42 grams, okay? Well, if you don't know this information, is 4 a multiple of 8? Yeah, so one paperclip could technically weigh 4 grams, right? There's 1 here and 2 there. But does 4 go into 42? No. What amount goes into each of these? 2. So what that must mean is there's 2 paper clips, each weighing 2 grams, 4 paper clips, each weighing 2 grams, and what's this one? 21, thank you, times 2 grams. Okay, so this is the same concept that Millikan did. He kept running his experiment and solving for Q, the charge that one of these oil drops had. And by using this logic, doing it many times and figuring out what the lowest common factor of all of these is, he was able to come up and work out what the charge on a single electron was. Okay? So let's do like an example. Okay, let's do an example here of a Millikan experiment setup. So let's give you some info. So here's some info. Okay, so a negatively charged oil drop is injected into a, I'm going to use this symbol for parallel, a parallel plate. Those aren't very parallel, but you get what I mean. To a parallel plate system. And the field is adjusted to 4.2 times 10 to the 5 newtons per coulomb. So what do we want to do? We want to do, mass of drop is, and of course you have to figure this out by knowing the density and the radius, 2.0 times 10 to the negative 7 kgs. What you need to do is to A, draw a diagram of this. Orientation of the plates is very important. B, find Q, and C, just for fun, find N elementary charges on the drop. Okay, so first things first. So we say the oil drop is negatively charged. So I'm going to draw it. There it is. Okay, if it's negatively charged, well, gravity we know is always going to point down. So how do we have to orient the field such that the electric field points up? Well, we are going to have to, let's draw the plates first. Ooh. Let's look at the curved corners. So if that's gravity pointing down, we know that we must have negative charge at the bottom and positive charge at the top, okay? Because we need to have an electric force that points up. And we have to orient it this way in order for that to happen. Okay? And if we know this is stationary, then we know that these two things are equal. Well, this is solved as Q times the field strength. I really want to draw curly E. It's hard to get out of that habit. And that this is mg. And that these must be equal because we know the net force equals 0. So Fe equals Fg. Q times that field strength equals m times g. And then we want to solve in this particular case what Q is. So Q is equal to mg over E. So we got 2 times 10 to the negative 7 kgs times 9.8 newtons per kilogram divided by the field strength, which I think I said was what? 4.2 times 10 to the 5 newtons per coulomb. Okay. And this should give us a value in terms of coulombs. So I'm just running the numbers here, and I'm getting that the Q on this thing, the charge, on this oil drop should be about 4.7 times 10 to the negative 12 coulombs. Okay, and the last question then that they're asking is, what is the number of charges that we've put into this thing beyond just neutral? So what we do is we take Q and we divide it by that elementary charge that was found by Millikan. So 4.7 times 10 to the negative 12, that's the overall charge of the drop, divided by 1.6 times 10 to the negative 19. This is coulombs per electron, coulombs per amount of charge, and this should give us NEs. Let's get about roughly around 3 times 10 to the 7 E's. And that makes sense, 987, we should be good. Okay, that's the kind of question you might have to answer with this. It's just a matter of making two forces equal and using that to find an unknown.